Okay, so we're going to spend this video looking at just this slide here because this deals with an issue that kind of goes against what we were discussing before, but you know, these are just minor exceptions to the Auf Bau principle, right? Now, if you remember, when it comes to determining the electron configuration of an atom, what we do simply, based on the past examples that we've looked at, what we did simply is add an electron to the available space that would be in a particular subshell or orbital, all right? So what we're going to look at is what happens as you go from scandium, right, to zinc. How do we determine the electron configurations for those particular elements in that region? And what you're going to see is that along the way, there are going to be certain exceptions that will come up. Okay, so we're going to start with scandium. So what you are looking at here is basically an abbreviated version of the orbital diagram of scandium, right? So the AR here basically represents the electron configuration of argon, right? And then you have the 3D sublevel, and then you have the 4s sublevel. Now, let me just say that the order of energy is actually not correct in this arrangement because it's the 4s sublevel which has a lower energy compared to the 3D sublevel, all right? So just keep that in mind as I'm going through this, all right? But apart from that, everything is correct, right? And over here, we have the same electron configuration expressed as the SPDF, expressed in the SPDF notation. Okay, so going back to this now, to get from scandium to titanium, what do? As we said before, we simply add an electron to what we have here. So according to Hund's rule, that electron will be added to the next vacant d orbital here. And then as we go from titanium to vanadium, we add another electron which will go into the next d orbital here. Now here's where the exception takes place. As you go from vanadium to chromium, what you'd expect is that the next electron would go here, right? That's what you'd expect. But it turns out that not only do we have the next electron going here, right? But one of these electrons here from the s orbital here will end up in the other vacant d orbital. So the resulting electron configuration is going to be what you see here, all right? Now, the reason why, it's a long story, to be perfectly honest, which we don't have time to get into, but just to summarize, the reason why is that it turns out that this arrangement here, where we have 5 electrons evenly distributed among the 3D orbitals, and 1 electron here occupying the 4s orbital, is actually, thermodynamically speaking, of a lower energy compared to this distribution here, where the 2 electrons would be in the s orbital and 4 electrons would be in the d orbitals, all right? So basically, what we're saying here is that if you have a situation where you can have a half-filled d subshell plus a half-filled s subshell, then that is more stable than the other alternative, which is this right here, all right? And that's basically a summary. It's actually a longer story, which, you know, would involve maybe 2 or 3 lectures, which we don't have time for, all right? Okay, so now that we have established the electron configuration of chromium, right, then to get from chromium to manganese, we simply add an electron to the 4s orbital because remember the 4s orbital is of a lower energy compared to the 3D orbitals, right? And then to get from manganese to iron, we add an electron to any one of these 3D orbitals, so we end up with this right here. And then to get from iron to cobalt, we add another electron to any one of these d orbitals here, so we end up with this. And then to get from cobalt to nickel, we add again another electron to any one of these d orbitals, and we end up with this. And then we get to another exception, because one would think that to get from nickel to copper, by adding another electron, then that electron would go here. But it turns out again that instead of that happening, well, in addition to that happening, one of these electrons here will move over to this d orbital, and the result would be this electron configuration. And you'll notice that in this electron configuration, there are 10 electrons in the d sublevel and 1 electron in the 4s sublevel, all right? And again, there's a long story behind this in terms of the reason why. Again, we just simply have to summarize here. And the reason why, in summary, is that the half-filled, let me just make a note of that here, the half-filled D sublevel, right, plus the half-filled S sublevel is of a slightly lower energy compared to the arrangement where the D sublevel has 9 electrons and the S sublevel has 2 electrons, all right? So those are the exceptions that you'll notice when you go from scandium to zinc. Let me just say here that to go from copper to zinc, all we have to do is add an electron, and that electron will go into the lower energy 4s sublevel, and therefore this would be the final electron configuration for zinc, all right? So that's basically what happens in the transition region. So things are not as straightforward. There are a couple of exceptions, namely in the case of chromium and copper, where the electron configuration is not quite you expect based on the trend, and we explain the reason why that happens. In the case of chromium, that's because of the greater stability of this arrangement where the D sublevel is half filled and the 4s sublevel is half filled. And then in the case of copper, this is more stable because the D sublevel, the 3D sublevel is completely filled and the 4s sublevel is half filled. All right? Okay. And then another point I need to make here is that these exceptions also exist for the periods below, right? So if you look at the periodic table, I don't have the periodic table in front of me, but if you look at the periodic table, you'll see that there's a similar arrangement in the case, I have a periodic table here. So the element that appears before or below chromium in the periodic table is molybdenum, Mo, and you'll see that there's a similar arrangement that is necessary for the stable electron arrangement for molybdenum. And in the case of copper, the element below copper is rhodium, and rhodium has a similar electron configuration in terms of 10 electrons being in the D subshell and 1 electron being in the S subshell, all right? Okay, so that's basically it for this video. I thought I should just spend one video talking about this so that you can review this because I know this can be a bit confusing, but that's basically how things are, all right? Okay, until next time.